Hi folks, starting up in a second. Sorry for the wait. Hey folks, welcome to COMP2300's lecture for today. Thank you so much for joining me here on Monday afternoon on this lovely week 11 day. Just going to check that everything is looking good in Restream. Make sure I'm coming across as a human being, which is good. Loading as usual. There I am. Seems to be right. Folks, welcome to week 11. We're continuing our tour through the topics in COMP2300. We're at the last topic of the course, the last official topic, which is returning full circle in some ways to what we were doing in week 1, where we were thinking about digital logic, logic gates, and how you might use logic gates to create a computer. So we did that. We got to the point where we were looking at something like a little simple CPU in a block diagram, and then we jumped into assembly programming, learning how to make a CPU do what we wanted it to do with our programs. But today we're going to take a step back to that first topic and return to the idea of the shape of a CPU, the features of a CPU, how it fits together, and what that looks like. So I'm just going to open up another window on the course here, so you remember what we're doing. This will be valuable in a minute. Before we start and get stuck into some content, I just want to point you to a few critical dates that are appearing. It is admin time. You know that your assignment 2 is due this week. The deadline for assignment 2 has extended to Sunday, 22nd, I believe. I'm just going to check that because I don't want to have the date wrong. It is 22nd of May. The reason for the extension was just to be out of order with another assessment task in other 2000 level computing subjects. I know that you have a lot of assessments due in the last 2 weeks of the semester. That's normal. Yes, it's stressful. No, there's nothing much we can do about it. But what we can do is make sure that at least within computing, we don't have too many overlapping deadlines. So the COMP2100 assignment is due on Thursday and Friday this week. And the COMP2300 assignment is now extended to Sunday to give you a few extra days. I know that doesn't suit everybody. People have work, people have other things to do on the weekend, but this at least gives you a chance to manage your time if you need it between these assessments and the other ones. People might have something else due on Monday at 9 AM. So for those folks, I suggest finishing off the 2300 assignment early and submitting it and making sure it's right, and then focusing on your other assignment that you've got to get done so that you can manage your time properly. I'm sorry, opening up the chat in case there's any questions people are going to ask me today. I hope there are. At team, join me live for architectures. Any questions? Chuck in the chat. we're up to week 11. That means we're up to lab 11, which starts tomorrow. And this week's lab is quite a bit different because you're going to be doing some programming in the C programming language, not in assembly. If you don't know what that looks like and have no idea what I'm talking about, have a look at the videos from the lectures last week. I did a demo on Thursday using the C programming language to create some little functions on the microboard, not the disco board, sorry, on the microboard. And that's what you'll be continuing in your lab this week, lab 11. The last kind of regular assessment task is due after the assignment, and that's actually the lab pack 4, labs 10, 11, and 12. Now that one is due on Wednesday, the 1st of June, so this is after week 12. You get a little bit of time in that week as well, but it's due just before the exam period starts. It's one of the best things you can do for your exam is make sure that you are prepared with your, or have gone through all of the lab work in COMP2300, and you also get rewarded for that by getting the marks for those labs. So I encourage people to make sure you do finish off all of the work in lab 10, 11, and 12, either in your labs, although I know because things can be hectic, it's difficult to focus in labs and get it all done when there are also assignments. You get some extra time after those labs. Haha, there's a good joke from Julian. If you don't know what C looks like, go and see in the lab this week. Haha, because C has two meanings. Let's get my little drawing thing out. I forgot that I had that. Hopefully it connects. There it works. I'll have to maneuver it onto my left side somehow. Okay, what are we up to today? And by the way, if I just go to the shape of the course, you can see that we're actually up to revision next week. This is the last week of new content, architecture and organization. Week 12 is only dedicated to revision, so we'll be going from top to bottom through the course material, covering things that you might have missed, refreshing them, making sure that you're aware of any holes in your knowledge. I've got a few extra lectures here which I don't give unless I have extra time for some reason or if they're required, but those ones are for your extra knowledge. Basically we're doing this week architecture and next week revision. You've also got 2 more labs. I'll just point to those. This week the C programming language, and then next week you're going to be creating a DIY operating system on your microbit, which is pretty cool. So that will be really pushing your knowledge of interrupts, timers, and context switching, putting that context switching idea into action. So it's a really exciting 2 labs this week. It's been an exciting 3 labs. All of them are not exactly aligned with the assignment, so sometimes folks aren't going to prioritize these until the assignment's out the door. I understand that, but you've got time to get them done anyway and get those marks, get that knowledge, and do well in the final assessments. I haven't talked about exam at all, but looking at the assessments page, you have the 2 last assessments, assignment 2, of course, lab pack 4, and the final exam. In the exam period, I don't think I've set the date here. The date is set on the ANU exam timetable, ready for you to look at. We'll get you more information about the exam soon, but you're doing the best prep you can for the exam by taking part in the quizzes, doing the mid-semester exam, doing the labs, and doing your assignments. So all of that work together is supposed to prepare you for the final exam. Of course, you can do some study, but I'm not expecting I'm expecting you to do most of your learning in the learning activities for the course, not in the study, which is for revision. If anyone can implement software mounted virtual memory, that would be cool. I agree, that would be super cool. That's going to be tough. So where are we up to? Week 11, architectures. And before we jump in with what this concept is of different features of CPU architectures and the terminology that you need to know, I'm just going to ask you, what is a computer even again? What are the parts of a computer and how do they fit together? And this course is called Computer Organization and Programming Execution, right? So if you ask yourself what a computer is, tell me those things. Jump in the chat and tell me what a computer is, what are some things it has, and what would be necessary to make one. I'll wait. I've got my glass of water here. I can just sip quietly. Computer parts, CPU and memory. Those are important parts. What else makes up a computer in your experience through COMP2300? A few more ideas. Clinking into my team. It's got to refresh every time someone. ALU. That's right. So that's a component of a CPU, isn't it? So we could go inside the CPU and start to find the components that are really necessary. ALU is absolutely. So fair game to talk about right now is anything inside a CPU or also outside a CPU that is part of a computer. And important, the USB port to plug it into is a joke from Julian, but I would say power supply, OS and hardware. All right, great. So what hardware? What hardware are we talking about? What hardware though? Buses. What's a bus? I should start writing these down. So we got CPU, wrong color, make it black to start with. CPU, memory, a bus, a collection of various accelerators like a clock. What? I'm confused. I don't think we need accelerators. What are these, like the pedal on a car? I don't know what you're talking about. Timer. And someone said clock, so I'm going to interpret that as timer, which is useful. Bus is going to be some connection between CPU and other stuff. That's right, exactly what a bus is, important. So you said high speed, I'm not going to put that qualifier on it, it's just a connection between your CPU and other stuff. Someone just said architecture. Well, you're just reading off the slide now. I want to know what are the components. CPU we had ALU, what are the other CPU components that are important to you? Other CPU components. Running out of steam here. Haven't we been studying this for 10 weeks? Tell me something about a computer. What have you learned about? Give me more, people. What have you learned about? Ooh, someone said NVIC. That's important. We've got to have, the CPU is going to be made of, well, everything here is made of gates. So logic gates, that makes up everything. Someone said a sequencer. I suppose that's going to be putting our code into sequences. Sequencer, we'll have a think more about that stuff later today. Probably some cache, some place to store. Something is coming in from memory, but we don't quite need it yet in the CPU, so it gets stored in a little bit of memory on the CPU. Someone said NVIC, but I'm going to just change that to just interrupts. We need to have some way on the CPU of interrupting it to get some kind of external attention on some peripheral. You're very slow. What about registers? No one said that one. Isn't that obvious? You use it every day. Registers, instruction decoder. That was important. Man, you guys are going to have trouble in the exam if you can't roll this stuff off. What's in a computer? Registers aren't real, says Julian. Yes, they are. RAM, that memory is RAM. That's there. Someone's saying that modern x86 CPUs actually have a very complicated instruction pipeline that does a lot because of the sheer size of the instruction set. That's a lot in there. I don't know what to make of that, but I'm just asking for things that are in a computer. So I guess you could say, you said pipeline. Well, we haven't really talked about that yet, but we could be talking about that later. I'll cut it off there. Maybe the next few slides might spur some of your memory, or you'll start to remember some of the things that you've talked about. You need a PSU, but that's true. I did say power supply though, I think. No, I didn't yet. Power supply. Okay, so we've got a lot of stuff that must be part of a computer. How do we put this stuff all together? Let's think about our microbit. The problem with the microbit, I love studying the microbit, but one of the problems with it is that it's like all stuck together. Here's one. Like, you know, there's all this kind of stuff on it, but you don't quite know how it fits together. And you've been looking a lot in the manual, but inside this, the computer on a chip, really, a whole computer is stuck in that chip. There's all these parts put together, including a CPU, memory, all the other bits and pieces that need to work together. So it's sometimes a bit hard to understand how it fits together when you look at the microbit. But if we look at a simpler kind of CPU, I've got some slides here which we're talking about the features of all of these different types of CPUs. Maybe you could think of them as architectural features, like every kind of building has windows and walls and roof. So that building has windows and walls and a roof. This building has windows and walls and a roof. They're all different types of buildings, like different kinds of computers, but they've got these core features which map across all of them, no matter what they are. So if we look at a very simple CPU, we could maybe see some of these features more clearly, because the microbit is even a bit too complicated. So let's look at a simple CPU. This CPU is called a 6502. Oops. It's a classic CPU from the mid-70s. And if you remember our OS slides last week, we were talking about computers going from mainframes to a mini computer like the PDP-11, which led to the development of Unix, because they were still huge, like a huge fridge, but they were small enough that a research group could use them and people could do experiments and be innovative and create new things. Then we were getting to what people called microcomputers, which was a computer which was small enough to actually have one person have it on their desk. And those computers were much, much simpler, and they were enabled by the development of a CPU on a single chip, rather than a CPU being on a whole board of chips. A CPU for a PDP-11 was a whole board you'd slide in, full of individual components designing it. But the 6502 was one of the first-ish generations in the 70s of CPUs on a chip. So not a computer on a chip or a system on a chip that we have now, but just a whole central processing unit with all of the different parts that we were talking about, the ALU, registers, instruction decoder, memory addressing stuff, all on the one chip. So this is a very simple CPU. It's an 8-bit CPU, so the one register is only 8 bits on this CPU, and when it accesses memory, it takes 8 bits at a time, not a full word or 32 bits of memory. A word on this is 8 bits, not 32 bits like on your microbit. On the microbit, there's the data bus, so that's for reading and writing to memory. Getting in and out, you get 1 byte at a time, D0 to D7, all the data pins. So each of those little pins would connect to a pin on a memory chip, which would be part of its memory. For choosing the address of something in memory, or in a memory mapped register from another kind of peripheral, you need an address bus, and the address bus is here, A0, and then it connects over on this side too, A12 to A15. That's the power supply, plus 5 volts. I think that's minus 5 volts. Oh no, those are ground. I think that's plus 5 volts. I've forgotten how you label these diagrams. So our address bus is these 16 pins. So whereas it has 8-bit data bus, it has a 16-bit address bus. And this was common in computers in this era, that you'd have a small data bus and a bigger address bus. if you had a very small address bus, for instance 8 bits, you'd only be able to address 256 bytes of memory, which wasn't enough for anything useful. So if you have a 16-bit address bus, that means you can address 64K of memory. Wow, 64 kilobytes of memory. Can anyone remember how much memory the microbit can address? Someone tell me that. Someone's saying that 6502 was using the NES. Was it really? I didn't know that. Oops. So, entertainment system. Sorry, I'm just fact checking some student in the chat right now. Sorry. What did it have in it? Oh yeah, fair enough. It was an 8-bit processor with some extra stuff on it. Cool. So my question was, how much memory is addressed by the microbit? Someone said a few hundred megabits. No, I don't think so. The microbit had a 32-bit address bus. It also has 32-bit registers, so they're the same now. And that means that it can address 4 gigabytes of potential memory. It doesn't have all of that memory wired in, but it has the capacity for it to be there. Yeah, so now, where are we? 6502 has this 64 kilobyte possible address range. What else have we got here? Because these are all of the ins and outs on the system. We've got this pin here, read write. That's going to say whether the data here is supposed to be writing to memory or reading from memory. So it can instruct the memory chips to either give it data according to the address bus or to take the data on the data bus and put it in the address, which is on the address bus. So you're either in reading or writing mode. NC means no connection, no connection, no connection. We got a few things here. These ones are to do with the CPU clock. This one is reset. That means start our computer again. And what else have we got? IRQ and NMI. Are those familiar? Those are interrupt pins. You know how many interrupts you've got on your microbit? There's like 16 core interrupts. Sorry if I'm wrong. And then the NVIC on the Cortex M4 can have capacity for something like 400 something possible interrupts. Of course, they're not all there, but there's obviously that huge list of interrupt vectors in your startup script. And the 6502 has a total of 2 possible interrupts. I guess you can call reset an interrupt as well, but that's a pretty brutal one. So there's IRQ, the regular interrupt, and then another interrupt called NMI, which means non-maskable interrupt. So the NMI always causes an interrupt, and the IRQ is an interrupt request. So that means that you can mask it, and there's a 1 bit in the control register for the 6502 that can mask that register. What's inside this 6502? Oh well, here's what it looks like. I've actually got one on my desk right now. If I oops, I've gone on the wrong page. Where's my remote control? There's my little 6502 computer. Make sure I'm in recording mode. I am. That's good. You'll be able to see on this. I'm just going to poke it with my pen here. There's the 6502. So it's not small really. 40-pin package. There's some other stuff here, so we need more stuff than just this CPU to make a computer, don't we? We've got a few other chips here. 1, 2, 3, 4, 5, 6 chips in addition to the 6502. So this one you can ignore because this and this thing over here, this chip is allowing me to control the 6502 from my computer. Uh-oh. Is it? Oh well. either way, if it's upside down or right way up, it's not hugely important. They're both fair. Oh yeah, see, it's my perspective to see it. You can see the writing on it. This way is the right way up to see the text on the chips. What we've got here, and I can just talk about all of the things here. This chip lets me interface with it over USB, so it's providing a serial connection. That chip is memory, regular RAM. This chip is non-volatile storage, ROM. You can see it's got a little window here because it's an old kind of ROM. Before Flash, there were ROM chips, non-volatile memory chips, but you had to go through a fairly detailed procedure to erase them, which is to put an strong ultraviolet light into that window for about 10 minutes, and that will erase it, maybe less than 10 minutes. Someone's asking if this thing is similar to the KL27 on the microbit. Exactly, it's enabling a serial connection. The ROM is an AMD chip, yeah. So to erase this, you have to put a special ultraviolet torch on there, and I don't have the tools to erase it. So I've just got the program on it, which came with it when I bought this little computer as a kit. It all came in separate parts, and they've included a program there. And then they've also got some RAM here, and the ROM and the RAM are sharing that 64 kilobytes of memory space. Although I don't think I even have 64K here. You can see this. Look at the date on that AMD chip, 1996. I think maybe it's an original old stock from that era. Anyway, one more chip. This thing is, it's hard to see what the words are on it, and they don't really help you at all. It's called a peripheral interface chip. So it's a chip which is going to help my computer connect to other stuff that's not memory and is in the external world. So it could connect to a keyboard, it could connect to some kind of other peripheral, and it's the one that's going to handle sort of inputs and raise and interrupt line onto the CPU. It's also memory mapped. So if you want to, if I'm on my 6502 and I would like to see what the status is of a GPIO pin, well, the 6502 doesn't have any. We saw all the pins before. There are no GPIO. The general purpose input-output are all on this peripheral pin for connecting to stuff. Julian's asking if it's like the GPIO. It's something like the GPIO. It's also something like those peripheral interface buses, like the advanced high performance bus on the Cortex-M4. But in this era, it had to be a separate chip. So these two together, they were like a power combo in the 70s. 6502, and that one's called 6821. There was another clone by MOS called 6522. This chip is manufactured by Rockwell, but it's a design by MOS, which I don't think exists anymore. And this one's manufactured by Motorola. Yeah, so that's my little computer. I've got a block diagram of it here so you can see how this all connects together. Here's the CPU. I know it seems like a bit of a wild, I'll turn my video off. A bit of a wild digression here, but I just want to be clear what a computer is, because I think that we have to be clear about some of these things. There's my CPU. There's my peripheral interface adapter. The PIA, the interface chip, has 2 ports, and in this instance, that's what the name of this computer, Replica 1. This computer has 2 ports, and one of them is going to be an input from a keyboard. PS2 is a kind of keyboard port, and the other port is output to a video controller. So this Replica 1 has a little yellow video connector to connect to a TV. And you can see that the 6502, as we learned, has 2 buses. It's got a data bus and the address bus. And so both of these buses connect to the PIA, and they also connect to the RAM and the ROM, EEPROM, electronically erasable, programmable, read-only memory. This one's not actually electronically erasable because you have to shine a big bright light on it to erase it. So I don't know what they're talking about there. Maybe some different replica ones came with EEPROM. There's a little thing here which says address decoding, because a few of the extra little chips on this tablet have the role of enabling either the RAM or the ROM, depending on the address that they see coming down that line. So if it happens to be like above 7FFF or something, that's 16 bits, isn't it? If it's above, greater than that, then we want to talk to RAM, and if it's less than that, we want to talk to ROM. So it switches the RAM off or switches the ROM off, and doesn't switch it off, just enables it or unenables it. A few questions happening. ROM stands for read-only memory. Exactly, as someone asked. It's read-only to the CPU. I can't tell the CPU to overwrite that memory. It's not allowed to. It can't. It's not that it's not allowed to. It's not electronically possible. It is possible to program the memory, but I need to have a bigger machine to do it. So in this case, I can use the little window on it, shine a UV light in there for 10 minutes or so, which will erase it. So all of the state of the little pins or memory cells is back to nothing. Tablet's on low power. Just go away. I think I'm good with my tablet being on low power. So I can erase it with the UV light, and then I have to use what's called a Rom Programmer, which is another physical device that you have to use special voltages to set up all of the memory cells to a certain state, and then it can be read by my CPU at regular voltages. I'm not quite sure how that stuff works. It's pretty old technology. This is stuff which was like early 70s, late 60s developed, and this is before Flash was invented. So if these people had Flash, there is no way we would be seeing that weird old programmable ROM. You'd definitely have a Flash chip that you can just electronically rewrite, just like the Flash non-volatile storage on your microbit. But because that wasn't invented yet, we had this other technology, which at the time they thought was super cool, because it was a kind of memory that you could program once. It would never run out of batteries or anything, and you could carry your program around with you. And in this case, it runs a few programs that are already built on there, which are kind of monitor program for the CPU to run something. It's not an operating system, but you can use it to run software, a interpreter for the basic programming language, and I think it has an assembler on there as well. I'm not sure. Yeah. The Arduino Uno uses EEPROM. Well, so does the microbit. Has EEPROM. Flash is a kind of EEPROM. What is this computer? It's called Replica 1. You might be wondering what it's a replica of. It's a replica of a little known computer called an Apple computer. This is an Apple computer. The Apple I, designed by Steve Wozniak and Steve Jobs in 1977, I think. And it has a 6502 microprocessor and a 6820 PIA. It's got some RAM. It doesn't have one RAM chip because RAM is expensive. Now I can afford, RAM is cheap now, but in these days it was expensive, and so they could get cheaper to get lots of small RAM modules and put them all together and then work out the addressing logic with these other chips. All these chips that start with a 7-4 probably contain 4 logic gates. That's the typical arrangement. That they'll have 3 legs, that'll be a logic gate, that's a logic gate, that's a logic gate, that's a logic gate. So that lets you set up a little system for addressing the memory. So I think each one of these is half a K of memory, 512 bytes. That's the Apple I. So that's what I'm talking about when I say a computer. Of course, we've got big computers now, but they share many of the features of this system. Back to the main lecture part. Now that I've got you oriented in what is involved in putting a computer together, what is in this system? Origins. Where do computers start? Well, in the early 30s, in the kind of interwar World War II period, people were interested in inventing calculating machines that became ever bigger. They had quite sophisticated analog computers that would use little gears and cams to do specific calculations for stuff. But people wanted to have digital computers, and they knew that it should be possible. They had some of the theoretic knowledge about how computers ought to work. So there was early ideas about how to create them. This one was a very electromechanical computer called the Zeus-1, the Z1 by Conrad Zuse. Relays, it had punch tape, a 1 Hertz clock, 64 22-bit words of memory, 2 registers, a floating point unit, and it was huge. Then these things became more electronic with a freely programmable computer with relays, 5.3 Hertz. Then we had this type of system, Eniac, in the 40s after World War II, so a first vacuum tube computer, not with electronic relays, which would have to click a physical mechanical switch electronically with a magnet. So vacuum tubes had something which was more like a transistor, but still this is something huge, taking up a huge room, or a building really, 167 square meters. And then came the microbit. Well, there are many computers in between those old things, and we looked at a couple last week. But in that early period, it was when people were starting to organize the components of a computer together in a way that made sense and could be used in many computers we've seen since. So there are, at that time, or in these early computer days, there were 2 schools of thought about how you should organize the parts of a computer. And there were the Harvard guys, the Harvard folks with their Harvard architecture, and they thought that it would be a good idea to have data memory and program memory. So they had this idea of a separation between 2 different kinds of memories. And in some sense, you could see separation on the replica 1, because there was a ROM, which was our program, and our RAM, our data. But on the replica 1, it all shares one address space. And there's just some logic in between there, switching those chips on and off. So it's not really separate. They're all in the same address space. In this computer, you have a different address space for the program and for your data. Another idea called the von Neumann architecture was that you would have one big address space that's going to cover both data and programs, and they'd all be mixed up in there. So you'd have the one single address space, one big chunk of memory, and sometimes there'd be some bits of this memory would be programs with instructions, and some bits would be data. And the cool thing here with this system was that it will allow a program to change itself. You could write a new program in this system, a program that could send out some data, which would be a new program. So the program goes in, data goes out, and there's a new program which can go in and make some more programs. So there's programs now all the way down. Self-replicating programs are possible here. You can see with this other design that that's not possible, because if you had a program here, if you have a program into the control unit, the output of that program is another program. Well, this second program is stuck in data memory, and you can't get it across. So there was sort of this initial imagining of what a computer could be. In this era, they imagined them as big calculators, or what we would think of now as big calculators, where you have a calculation that you want done on some data, and you need it to happen very fast. So you make a big calculator that does it powerfully and quickly. But in that imagining of what computers do, you would never need to take your output and turn it into a new program, because you would have written your program by hand, because it's just the representation of your calculation that you've carefully worked out, and it operates on data and produces a result, job done. The other imagination was that you might have programs that want to write new programs. We call them now things like compilers as a program that writes a new program, or an assembler. And so those things wouldn't be possible with the Harvard architecture. So as it turns out, this is really the model which became dominant, where you'd have one single address space. That said, sometimes within a CPU, you have some slightly different address spaces internal to the CPU inside memory cache, where it's preloaded some instructions and preloaded some data, and sometimes people refer to that as modified Harvard, but the address space is still unified most of the time, unless they're non-unified memory architectures, which is another modern concept which we might come to eventually. But this is all to say that even though, if anyone tells you that there are two simple kinds of computers, it's probably not the whole story. Someone's asking me some questions, which are probably very salient. The Z3 and Z1 and Z3 before Turing made the thing to crack the Enigma. They were, I think. Turing's thing to crack the Enigma was during World War II, in the 40s-ish. So Z3 is 37, Z1 was 37, and Z3 was 41. These are, I think they were German computers, so unfortunately they weren't smart enough to use them for designing codes. What if your calculation was recursive? You'd need this self-replicating program. No, it doesn't. That's not what recursion means. It's not a self-replicating program. Good try though. So let's have a look at our simple CPU. Remember this diagram? We had some memory. And we had an ALU that had outputs to some flags and outputs to some data management module. And we had some registers. And we had some kind of thing that would be decoding and sequencing different kinds of the code coming in from the instructions sequence within your memory. We can actually look at this on our 6502 as well, because I've got the data sheet for my 6502. I'm obsessed with the 6502 this week. Sorry about that. If you don't like 6502 stuff, then I don't know, tune out now. It's a simple. 6502 is a very simple CPU, so it's got a simple data sheet. It's not 900 pages like the Cortex M4. It's 15 pages only. So there's different versions of it. And here's a picture of what the architecture looks like. Instruction decoder taking instructions from the instruction register, just getting ready to be brought into the CPU. We've got a buffer for data coming in and out. We've got decoder there, some kind of timing control, which is loading up instructions and then operating, loading them, executing, loading and executing. We've got some interrupt logic, which is going to send in a message to the instruction decoder to say, stop, do something different. Someone's just had a realization that we have two registers here. In fact, there are three. Sorry, there are three. Actually, maybe five. Let's count them. Where are our registers? There's our ALU. There's one, index register Y, index register X, the stack pointer, that's 3, accumulator, that's 4, and then PC, and PC comes in 2 halves because it's 2 bytes, sorry. So there's low and high, so that's 6 registers. Only one of these is general purpose. ALU is general purpose. The index registers are, you can use them to sort of store data for a short amount of time, but the index registers are really used for doing offset addressing. So you'd take one of those index registers as the base address, and then your offset would be stored in the accumulator, and then you can do an offset address to load up some data. Am was talking about the Z1. Yeah, 2 registers. Well, indeed, we've got a grand total of 6 here on the 6502, and only 1 general purpose one and 2 special purpose ones. So that's it's a bit of a different scenario. You can see these are all of the possible instructions on a 6502. You've got your typical ADC. You remember that one. You know how that works. and arithmetic shift left. That should be, you should know about that. We've got a few cool ones. We can do not loader, load register, load memory to register. We load memory to accumulator, and we can load index X from memory and load index Y from memory. And then that's logical shift right. There's NOP. There's OR. There's some push and pop to stack, but only for the accumulator and processor status register. The processor status is the flags. This one, NV, nothing, break, decimal, IRQ, mask, 0, and carry. There's a few other weird registers, weird commands. You can decrement and increment registers with a single instruction. And you can also do one cool thing, which is go into decimal mode, which allows you to do calculations as if we're talking about decimal numbers. So it just takes each, if the 8 bits of the data bus, the lower 4 is the lower digit up to 9, and the upper 4 is an upper digit up to 9. So you can calculate things up to 99 in 1 byte. Weird. Anyway, that's our 6502. I'll go back to the lecture now. We won't see 6502 for a little bit. So we're talking about a pipeline now. So the idea is that we've got a sequence of events in our CPU from things going in from memory, an instruction going in, being loaded into code management, being sequenced and decoded and sequenced, doing something in the ALU, and then sending the output. And there might be an idea that because these parts of our CPU are actually different components, we might be able to overlap them a little bit. So while one instruction is on the ALU being executed, another one is being loaded in. And this idea is called pipelining. So you get overlap the things that are going on in your CPU to increase the throughput of your system. So a way of imagining pipelining is to imagine an escalator. When you go on an escalator, it's not like one person stands on the escalator at the bottom and then there's a queue of people behind waiting for that person to get all the way to the top before they start, right? We have one person on the escalator here, and there's like one person on each step. And sometimes there's 2 people on each step, right? Because or probably not 3 because it'd be dangerous, but 2, it's like dual cores. Each handrail is a core. And we can get very high throughput on an escalator by people going on every step. So we can do that with a CPU as well. And in fact, we do this in the Cortex M4 on your microbit. Because you can take the 3 steps of the Cortex M4's instruction cycle, which are to fetch instructions from code, decode them in a decoder, and then do what they say, and do them across 3 clock cycles. So this instruction starts at 1, we're fetching this instruction, then we decode that instruction, then execute it. And when we're decoding instruction 2, we fetch that one. When we're executing instruction 1, we're decoding instruction 2 and fetching instruction 3. So this is from the manual for the Cortex M4, and it says that you can fetch up to 2 instructions with 1 transfer, because the Cortex M4 can load from memory 32 bits at a time. So if they're only 16-bit instructions, they can be fetched together. There can be some cycles in between when the CPU decides to actually decode and execute things, and then they typically do these in sequence, 1, 2, 1, 2, 1, 2. It says also in the manual that there might be situations, conditional branching, where your pipeline might get broken because it might have fetched two instructions, but this one is saying branch to a different location or conditional branch somewhere else. Yeah, so we can't cope with every single situation. If we're in a situation like a conditional branch, where the next instruction isn't known until this one finishes executing, the pipeline is blocked and these ones aren't going to execute. So they have to do this so-called flush of the pipeline, which is where you take your escalator full of people and then just get a fire truck to just set the fire hose on them and blow them all out the bottom and let them up one at a time again. So that's what a pipeline flush is like, or it's what I imagine it to be like. It might not be so traumatic in your microbit. So someone's just raised in the chat this idea of conditional branching possibly being bad for pipelines. And in fact, there are a number of different... Everyone's jumping ahead with speculative branching. Ah, come on. Don't jump ahead. You're not supposed to know about things until I teach you. Well, you're allowed to, I'll give you that. You're allowed to know about things until I teach you, and then I'll reinforce them for the whole class. No, there are a number of different things which can go wrong with this pipelining idea, and we call them pipeline hazards. There's a specific terminology for them. So a pipeline hazard is some kind of situation, sorry, excuse the baby sounds. The hazard is a circumstance that prevents a pipeline from working correctly. So you might like it to be 1, 2, 3, 1, 2, 3, all very neat, but it could be that there's some reliance on data from one outcome to do the next instruction. Maybe you've been changing a number in a register and then you use those registers to do something else, so they're reliant on previous instructions. So there might be a data hazard. There might be a structural hazard where one part of the CPU is required by 2 instructions simultaneously. Not so much a problem with Cortex-M4, but maybe your memory can only fetch one thing at a time. There might be only one way to fetch memory, which is typical. And then there's a problem if 2 instructions are trying to do that at the same time, or one fetch might take a long time for some reason. There could be a control hazard, which is the one we've been talking about, where a conditional branch means that the location of the next branch is unknown until that instruction is executed. How do you deal with these ones? A few options. This one is like leaving little spaces between the people on the escalator. So you have a person, and then a bubble, and then a person, and then a bubble, and then a person, and then a bubble. Another way of doing this would be, or to deal with the structural hazards, I suppose the bubble idea could help with data, right? Because you might have some instructions that rely on the other. If you space them out, you'll get those values coming back. This idea of branch prediction, where a CPU might just run ahead and see, I've got a conditional branch. I'm just going to execute some things in case in different locations that I think that the branch is going to go to, just to see what's going to happen. And then if we end up taking one of those branches and I've already calculated the answer for that, then good, we're ahead. Branch prediction can be bad if there's some kind of hacker exploit that enables it to the CPU to execute some code that it wasn't supposed to, because you're exploiting the way the branch prediction works. And that actually happened, and it meant that some Intel CPUs work more slowly than they were supposed to, because they had to have little updates in operating systems to turn off certain features that were turned out to be exploitable. Another issue is out of order execution. So you could have a certain order of instructions in your program. Maybe the processor sees those and is like, wait a minute, that's not the optimal ordering. I can just do this, turn it around, and then that will work much faster. So there are downsides to all of these. You can read about them if you wish, but the downsides tend to be on 2 sides. Either it makes things slower, or it makes things exploitable by hackers. So we have to be very careful with the way these things work. Out of order execution. No, you're out of order. This whole damn CPU's out of order. It's a meme from a famous movie, which I've just forgotten right now, the name of the movie. Someone can remind me the movie in the chat. I remember the name of the movie yesterday, and now I have forgotten it. But this guy is a lawyer, and has been stuck in a bad situation, and he says this whole court's out of order because he's realized that he can't get out of his bad situation and he loses his temper at a lot of people. Out of order execution. So reordering the sequences inside the pipeline, inside this area. We've already loaded up some code. The sequencer is deciding to put them into different places, and we just switch around which one we're pointing to. Here's an example of a calculation. So you might have a simple function, f of a, b, and c is in brackets a plus b times c. Seems simple enough, right? Well, let's load up a number. That's going to be a, is in OX2000. Then we'll load up b, load up c, and now we add a and b, and then multiply these together. This seems good, but the issue is that you can't do this one. You can't do this one until this one comes back, and you can't do this one until you get this one and this one. So it might be possible that we could reorder these so that this one is delayed a bit until we finish this one taking place. So we can switch around these two lines of code so that this one is doing the load for A and B, that's A and B. Then we're doing the bit of code that requires A and B. Meanwhile, we're loading C, and then we're doing the multiplication right at the end. So if we had to overlap these things, this one might work better because we're not relying on the outcome of this ALU calculation to run this final line. Doesn't seem like magic, but it all is pretty magical. How do the bubbles help things? Well, there was a picture of a bubble here. That was a bubble. So if you need the outcome of instruction 1, I mean, in this three-stage pipeline, it's unlikely that this would happen, but if you needed the outcome of instruction 1 to actually fetch instruction 2, you could have a bubble here where this one was fetched all the way up here. So if you knew that that did the decoding and realized that that was going to be a branch, you might not bother decoding until there. So you can insert a bubble up here to push that one forward. Three-stage pipelines, it's hard to imagine the things going wrong so much, but I think on the typical x86, 64 processors that you have in your normal desktop computer, there's like a million stage pipelines. Not a million, but many stage pipelines with lots of complexity. So it's not as much of a problem in the simpler CPU like a Cortex M4. Oh yeah, so now we're done with this pipeline part of the talk. I'm going to talk about multiprocessing. Multiprocessing. So this is a funny thing. It's multiprocessing. It makes it sound like it's complicated and difficult and esoteric, but it's what every single computer you have does. I doubt that anyone here has a actual thing that we could call a computer, a phone, a laptop, a desktop, a Nintendo Switch, a PlayStation, that doesn't do multiprocessing all the time, because multiprocessing is basically the idea that you will have multiple CPUs of some kind, any multiplication of CPU units to do tasks. Now, up until the era, I mean, if we look at CPU eras, I'm just going to follow the Intel ones. There was the Intel 8086, which was better than ones like the 6502, which was earlier. That was a more complicated thing. This came out in like 1979 or something. Then there was like all of the 86s, the 286, 386, 486, 586, and they started calling that one and gave it a name Pentium. And then they had Pentium 2, Pentium 3, Pentium 4, and that was now like the late 90s. All of these systems had one CPU, so we can call them uno processors or mono processors. One CPU, just like your Cortex M4 on your microbit. And then ever after that, they started. I'm just talking about Intel. They started inventing things called the Core processors. Core 2 Duo was a kind of CPU. I think that's what I'm not sure what the first one was called, but that would have a two CPU processor. And ever since then, in the 2000s, there have been multi-processors on your desktop. In the 90s, when there were CS students learning about computers, they would learn this stuff, but they would have to imagine like these mysterious, huge, complicated supercomputers, which would be multi-processors and have different technologies for doing it. But now for you folks, learning now in 2022, all of your computers are multi-processors. So it's not esoteric at all. And the problem I have with this is that a lot of the textbooks that you might read were written in the 90s. So they have or the first edition was written in the 90s. So their perspective is that students shouldn't know about multiprocessing being the normal thing. But for now, like your watch has multiple processors. It's like totally normal. Anyway, I digress. I think this is my rantiest lecture. Someone says they own an old ThinkPad with a single core. Yeah, it must be old to have a single core. There's a couple of kinds of multiprocessing techniques that we will discuss. This first one is, I guess you'd call it vector processing, where you kind of multiply parts of your CPU to enable it to do the same instruction on multiple bits of data at the same time. We often call that SIMD or SIMD, single instruction multiple data. So a SIMD CPU might replicate the ALU so that you can set it up with a single instruction like add, and then within your memory you might be able to take, there's one word of memory, and there's the second word, you're going to add these together. Normally you just do one add with the whole field, but now we're going to split them up into maybe 4 little ones, and we'll add each one. And your microbit can actually do this. It has some SIMD instructions. It's only a 32-bit processor, so it can't do very much, but it can do a bunch of arithmetic with 4-bit fields in a 32-bit register, 4 8-bit fields, or 2 16-bit fields. And it can do some crazy things like add and multiply things together. These things were really useful when they, now and when they first came out, for doing special kind of sort of signal processing and multimedia graphics and audio and signal calculations, which is what they're still used for now, kind of digital signal processor extensions. MMX is an early one that was, I think, multimedia extensions is what it was called on the Pentium 2. SSE is a bit later. Neon is an ARM thing, etc. So it's, to use these things you have to know you want them, and perhaps your compiler might have to be set up to expect that in a certain circumstance it's going to use these special instructions. But once you know how to do it, you can have huge efficiencies, because with one instruction cycle you could be doing 4, for instance, values, treating 4 different values. And if you have to go through a lot of different values in a sequence with the same simple instruction as you might have to do with sound or video calculations, that can cut your processing time by 4 easily, if it's possible. Another idea, hyperthreading. This is another thing which is typical on modern CPUs. So the idea of hyperthreading is that you replicate another part of your CPU. Broadly speaking, you replicate the registers, the flags, and the code sequencing and decoding parts, but you keep all the other stuff the same. And basically that means that you can have kind of two CPUs, but they're sharing the same ALU and data parts. So you could have one program running here, or one thread, as we talked about last week, and another one running here, sort of switching between them as needed. You'd often see that on a modern CPU. You'll see that it has 6 cores, 12 threads. That's because it has hyperthreading for each of those cores, allowing it to switch in 2 threads. Tricky stuff. We could talk about this in a minute, but I'll get you to have a think of some workload that would be helped by SIMD and one that would be helped by hyperthreading that I haven't already discussed. And you can chuck it in the chat. Now, multi-core CPUs. So this idea was that on the same package, as we discussed last week, on the same silicon wafer, you can have multiple CPUs, maybe 4, maybe 6, maybe 8, maybe 12, maybe 32. So you have the whole thing replicated, 1, 2, 3, 4. And this is where we get to the modern situation, which is that you have a bit of all of these things. You've got multi-core CPUs. Each one of those CPUs might have hyperthreading, and each one of them probably has some kind of SIMD operations, replicating the ALU. Hyperthreading is not universal. For instance, your microbit doesn't have hyperthreading. It only has one kind of multiprocessing option, which is SIMD. Someone can already imagine multiple choice questions about this stuff. Ooh, maybe someone's saying something beneficial to SIMD would be servers with a real-time workload that need to take in a lot of requests. I would say that's more of a multi-core or hyperthreading situation. Because if you have to take a lot of requests, you might have a processing time for each one, but you can send them off to lots of threads. So it's handy to have a multi-threaded server. That's not going to help SIMD so much because they might come in at slightly different times and they would each have a slightly different requirement. So really, what have we got these days? Yeah, so hyperthreading not universal. My desktop over here with its AMD Ryzen CPU has hyperthreading, has 8 CPU cores, has a bunch of SIMD extensions in various types. My laptop, for instance, MacBook Air with a Apple M1 64 chip, I don't think it has hyperthreading, but it also has 8 cores, and I think it has 8 cores, is that right? Yeah. And SIMD. But the cores are faster. So I've told you a lot of data, and maybe you're wondering, is there some way to integrate this all into one framework? And there is. This guy, Mr. Flynn, I suppose, Flynn came up with a taxonomy, which is a framework for naming things. That's what a taxonomy is. It's to do with names. Flynn's taxonomy from the 60s, right? Still relevant today, invented in the 60s, to classify the functionalities of a processor. So this came out in the 60s, and Flynn was not imagining that we would all be walking around in our pockets with multi-core hyperthreading SIMD processors. They were imagining, computers within the framework of the time, which was mainframes and mini computers, as that is the big fridge style. Whoops, I've lost my pen now. And you would have really these, maybe the vision in the future that maybe people will have their own computer, but not in the short term. So there are 2 dimensions for this taxonomy. Single instruction, multiple instruction, so the number of instructions that are happening simultaneously. Single data, and multi-data, multiple data, the amount of different data objects which are being operated on simultaneously. So single instruction, single data is the standard uniprocessor 6502 boring old school CPU system. Nothing wrong with it, but it's just running one instruction on one thing at a time. One thing at a time. Single instruction, multiple data, SIMD, that's our SSE and Neon extensions, and also Cortex M4. I've forgotten what they're called, something like DDSP. They're just regular instructions. You can use them if you want to. I think we did an example with them, didn't we, earlier on? SIMD, TVB. I must have lost it. Oh well, we'll find it and do an instruction on Thursday, example on Thursday. No, I can't remember. So which of these are common? Oh, we haven't got the second one. Multiple instruction, multiple data. This is our now multi-core processors live in that area. And then there's this other weird one, multiple instruction, single data. Like you're going to take two registers and you're going to AND them and add them at the same time. Why would you do that? So it's a bit mysterious why this one lives here. There's a funny taxonomy because you've got three really useful parts. 75% of it, totally good, understand it. 25% of it, what? Does that really describe any processor? And every year I ask this, I ask people to go and find an example of a MISD processor. And someone always comes back with something like on the space shuttle, which is an old kind of spacecraft we used to have before they started exploding. Maybe there was some special computer which would do multiple processes, multiple calculations with single data simultaneously for some reason. But it's pretty, if you just can only point to the space shuttle, that's a pretty obscure reference. So if anyone else can find another MISD example, I don't know, you get a Piazza point, which is not useful for anything, but you can feel good about it. Yeah, so this one, SysD, uniprocessing, typical of normal, boring, simple CPUs, which we would now only use in embedded applications like a fridge or a toaster. SIMD, useful in most CPUs for doing different kinds of signal processing calculations, even your microbit. And MIMD, totally useful for multi-threaded parallel tasks on all types of regular general purpose computers, from laptops, phones, to supercomputers or the mainframes that we have today. Yeah, so someone's saying that any system where you need redundancy, it would be maybe useful to have MISD or multiple instruction single data. I suppose so, yeah, but it's always difficult to point to one. This question, is hyperthreading good if you need to manage two different programs with different contexts? Yep, you can do that. So it's not as good if you had two separate CPUs to run your two different programs in parallel. That's obviously very good. If you've got one single CPU SISD, that's going to be slow because you've got to shift the whole context switch to get to your other thread. But you can get into a happy in-between place if you've got a CPU plus hyperthreading, because if you do a context switch on that kind of CPU, you don't really have to do any switch. You don't have to put things on the stack and take them off again. I'll just go back to the hyperthreading example. If you've got two threads, thread 1, thread 2, or application 1, application 2, the only thing you have to switch is which of these applications is talking to the ALU. Because they've each got their registers. Their registers can stay in the same place. Flags can stay in the same place. We don't have to use the stack. It can be faster than a big full context switch. Has it been a big talking lecture? I'm just going to keep pushing through this content. I want to do a demo with my Replica 1, but something went wrong with it and I don't know why. I'll have to debug it. So I'll get back to you on Thursday with a Replica 1 demo. Sorry about that. We'll have fun on Thursday with it. You know what I think it is? The stupid Linux permissions for things. I hate that stuff. Permissions for USB devices, because I remembered as I was starting the lecture that I'd never, or as I was trying to get it to work, I've never used this serial device on this computer before, because I got this computer just after the last time I taught 2300 in 2020. So I did do a Replica 1 demo on a different computer, but now that one's not here, is it? That's not very useful. But we get some more content about cool parallel computers, and we'll talk about some more stuff on Thursday with more demos. Amazing parallel computers of today. So again, this goes back to my bugbear about this stuff, that the textbook teaches you about uni processors that don't really exist in your normal experience of cool computers. So, and they talk about parallel computing as if it's something that only occurs in mainframes, which is crazy, because an amazing parallel computer that you have today is your phone. Everyone's got a phone. This is an old phone with an app that I was designing some years ago as part of my research. It would be a sort of music app, you scribble on it, it does some stuff. But this phone had that, there's an iPhone 8, which is old now, right? It's a few years old. And it was a 6-core phone. 6 cores in one phone. So all of the things that you've got, or all the things that we think are really cool, multiple instruction, multiple data, got that. It's got SIMD because it has the ARM chips with the some ARM vector extensions. So it doesn't have hyperthreading, no, but it doesn't need it because it's got 6 cores, right? And it's only a phone. And all of the normal phones you've got, the regular ARM chips, have really become very good at being multi-core systems. And there's a reason why, particularly in phones, and particularly with ARM chips, it's good to have multiple cores. And I'll show you why on the next slide. ARM is a company that designs architectures for CPUs. They don't make CPUs. Other companies make the CPUs, like Nordic Semiconductor, who make the ARM Cortex M4 in your microbit, or Apple, that makes the chips in your phone, or maybe NVIDIA makes the chip in your Nintendo Switch. And they had this idea of an architecture which would have different kinds of cores. So on my AMD Ryzen computer, or maybe your Intel computer at home, you might have lots of cores that are the same, essentially. But ARM had this idea of heterogeneous computing architectures. So heterogeneous means different size, or different core computing architectures. So the idea was that you'd have some little cores which would be efficient and power saving, and the idea is you use those most of the time. And then you have some big cores that are powerful, but they need more power to run, and you just use these when you need them. And all of these cores have the same memory regions, and then the scheduler would be smart enough to execute threads on the correct core, or move them between cores as needed to make the best use of the power of the big cores while not using too much battery power. And this is going to be really useful on a phone because you've got limited power. Limited power in your battery. So the Apple A11 had 2 big cores, 4 little. What about the Apple M1 on my laptop? 8 cores, that has 4 big cores and 4 little cores. And they became better as they went along. So, you know, the story is a bit weird. Like, Apple got to be so good at making these things for their phones and iPads that they just made them a little bit bigger and put them in their laptops, and they're just great for battery power, because when they're running on the little cores, they're really just sipping battery power. So it's quite an amazing, cool concept, this idea of big little computing. It's really changed the game for the potential for battery life. Someone's asking me a question. I'll try to answer it. Yes, too big and full. It's a letters and numbers joke. That's going way back. I don't think there's any... Oh, there's celebrity letters and numbers, isn't there? I still think of letters and numbers as just like the Richard Moorcroft old version. You probably don't know who that is. Another amazing parallel computer of today, your gaming PC. If you have a GPU that looks like this, that thing has got a lot of cores. It is a parallel computing beast. So these are a couple of GeForce RTX 2080s. It was new GPU day in the lab some years ago. TI, I think. So the idea of a GPU architecture is taking this SIMD idea to an extreme, right? On a CPU, there was the idea that you could get a graphics or signal processing pipeline sped up by having one ALU process a couple of different things at the same time. And then on a big graphics card, they want to speed up a pipeline of huge amounts of pixels having the same operations going simultaneously by just having heaps of ALUs. Someone says Intel implements big little on x86. Cool. We've got an Intel fan in the chat. Am I offending someone? Yeah, I wonder what the Intel big little... Oh, it's like their 2021 computers. Yeah, the Intel folks and AMD folks are really head-to-head improving things with more cores, basically. But we're talking about an i9, which is like a very expensive processor. Anyway, back to GPUs. The idea with a GPU is that, or inside these NVIDIA architecture, I don't really know anything about the AMD GPU architectures, or indeed the ARM GPU architectures that are in phones and switches and other things, but there's a lot of info about AMD CUDA stuff, and you might study it if you go and study parallel or high performance computing. But in the NVIDIA CUDA architecture, they've got a thing called an SM, which is called a streaming multiprocessor. And this has lots of cores, which are kind of ALUs. So here's one SM. It has 4 different cores, 4 processors, and then it's got lots of these tensor cores here, and it's got lots of these little registers. I think that's what those things are. No, I don't know what they are. Anyway, these things are all ALUs in there, I think. All ALUs. Tensor cores are specific ones for doing specific multiplication and addition operations. And there are tons of them. So, and this is I don't know what it is, a Tesla V100 GPU, which has 84 of these SMs. So that was one SM, which already had heaps of ALUs in it. And now we've got all of these different SMs in different little blocks. And then a huge cache, and then some huge connections to memory at either side. A lot of buses happening in that GPU. So the GPUs are super parallel computing beasts. 500, the Tesla V100 had 5,376 cores. That's a lot. Tensor cores, I suppose. Maybe. Some kind of core, anyway. That's a lot of stuff. A lot of pixels got to be processed at once, or a lot of bitcoins mined, or a lot of machine learning algorithms optimized? Question in the Slack. Someone's mentioning fun facts in the chat. You can use RTX 3080s on Raspberry Pi, but they don't have drivers. But someone's asking to clarify what does GPU do exactly. Goes between your CPU and your screen. GPUs do a lot of stuff. There's two things here. Sorry, maybe I've jumped the gun. What is a GPU? Graphics processing unit. Graphics processing unit. It is usually used for making things that your CPU wants to go on a screen, go on a screen. And they've become very powerful in order to play complicated games that want to do a lot of graphical processing. And graphical processing is a very highly parallelizable task. So GPUs have become very sophisticated parallel computers. Now, by the by, once they had started to do this, people realized, wow, we've just made supercomputers that everyone has on their desk. What if we use this parallel power to do other stuff? And so there are programming frameworks where you can use a GPU to do stuff which is not exactly related to putting pixels on a screen, but is a very parallelizable task. And one of the things included in that would be mining cryptocurrency. So often people who are gamers who are trying to buy a GPU complain, oh, the crypto miners have bought all the GPUs, so they're now all really expensive. Because if someone wants to mine cryptocurrencies, they need a lot of GPUs to do that because they're super powerful parallel computers. The other thing you can do with GPUs, which is really useful, very usable or very parallelizable task, is to train machine learning algorithms. So when people are doing machine learning research, they often buy a very powerful GPU to help do their research because it can operate these very parallelizable algorithms quickly. Yeah, so I hope I guess the second half of the question was, what does a GPU do exactly that needs all of this? Well, V100s are V100. That's a server GPU, so it's actually not. It's not going to be driving a screen or playing games. It's going to be training machine learning production algorithms that need to be trained quickly and at scale in servers in machine rooms, doing a lot of work. So I don't think this GPU even has a graphics, doesn't even have an output like for an HDMI thing or anything. It's just doesn't have anything on that side. Normally on a GPU you would have little plugs for to plug your screen in, but these kind of GPUs don't have that. And you can see it looks like a really chunky thing. It's quite big, it'll be about that big and that thick. It's mostly heatsink and then a really giant chip, because these systems have a lot of stuff on them. They've physically got a lot of transistors. The chip on them would be quite large. Not that big, just fairly big compared to the little 6502 and the little chip inside your computer. Anyway, amazing stuff. What else can you use to create a computer? Any questions? There's some questions in the chat which I think I'm talking about. We might get back to them another day. You can make a computer out of plastic. This computer is called the DigiComp1, and it has a 3-bit output. You can program this computer by putting these little pegs, little tubes on little plastic pegs, and then you go clink, 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 clink with this mechanical mover, which does operations. It's just a toy, really, but it's a cute thing. It says on the packet, the first digital computer in plastic, which is, I would say, is a highly an optimistic kind of claim that it's a real computer when it can only do a 3-bit calculation, A, B, C. There's 2 bits in and 1 bit out. There's another cool kind of computer. This is another alternative architecture, which is not the same as these other things we've been looking at, but the idea of a multi-core computer that would work with each core going kind of in a sequence. So this thing was called a Propeller by a company called Parallax, which would have 8 cores, and each core would have its own memory. And then there'd be some shared memory, and it would move around the program counter would move around the cogs. Each cog would be a different processor core. And these CPUs aren't actually, they're not actually that esoteric, because in fact I have one on my desk. If I just go back to GP, you can see that. There's the little propeller hat. That's a Parallax Propeller processor. They were quite popular in the zeros as a kind of microcontroller processor for different kinds of tasks. In the hobby world, they're sort of completely blown away by Arduino using Atmel chips. So they're not that popular anymore, but this design, the replica one, I think this computer design came from about 2002. So at that time, the Parallax was a pretty popular microcontroller for hobbyists, among other tasks that microcontroller processors are used for. But a cool idea. I don't know anything about how to program for them, by the way. I only use the program that this one came with, that the firmware that the creator of this replica made. And there's a demo video of these things if you want to see them. There's a few other architectures which I haven't talked about at all here. One thing about ARM architectures is that they've sort of taken over the mind share for a way of designing an instruction set called reduced instruction set computing. And ARMs are sort of an example of a RISC architecture. This is sort of in contrast to the x86 Intel architecture, which is really complicated. It's often called CISC, complicated instruction set or complex instruction set computing, which have a lot of instructions, but even compared to x86, even with all the instructions that your Cortex-M4 has, it's still considered to be a fairly tight ISA. But ARM make their ISA for profit. So there's been efforts to make a sort of open source ISAs, and an example of this is called RISC-V, which is quite popular, and there are, you can go and get a RISC-V board and a CPU and play with it, which is a lot of fun, and people often say, oh, this is the next big thing. So maybe it is the next big thing. Maybe eventually we'll have RISC-V CPUs in our desktop computers, but not for now. Ooh, questions? Not really questions, it's discussion. The other one I haven't talked about is x86 or AMD 64, which is the ISA designed by AMD to extend Intel's x86 ISA into 64-bit processors, later kind of back adopted by Intel. Yeah, these are instruction sets that you will probably come into contact with if you keep doing your computing courses, and you will find that they're annoying and complicated compared to ARM. And I'm happy that you've all worked on ARM. I got in trouble in a meeting, well, a little bit of trouble, because one of my colleagues said that none of our students know anything about assembly programming. And I was like, well, what do you mean? We're all doing assembly programming in 2300. And what he meant was x86 assembly programming. And I suggested that the obvious solution was just to change his course to use ARM64, which turned out not to be possible. It was a joke, but a fun thing to imagine that the obvious solution was that. Oh yeah, a cool thing. So we're going to look at this little web browser of a simulation of an early ARM chip. the ARM1, the first ARM chip, the ancestor of all smartphone chips and your microbit. I wonder what other slides I have. I might wrap it up in a minute. Yeah, we'll do this Replica 1 demo later. The last thing we'll do is this ARM1 simulation. Ooh. Can I make it bigger? So, here's this ARM chip. Color. It can do some stuff. I wonder what it's doing. You can probably give it some code. If you look around the internet, there's a lot of simulations of simple CPUs, even with this cool visualizations as well. This one's particularly beautiful because it has like the onboard layout of the CPU as well. And these little pads are what's going to connect by a tiny little wire to the big leg on the side of the CPU. And if you want, you can see the size of like the silicon die in one of these things, because it's right here on my desk. You can see that little square inside there, that's a silicon die for this ROM chip. But you can, if you look closely, probably not in this video, but you can see in the pictures some tiny little bond wires that are connecting those legs from the silicon die to the legs of the chip package. Probably the ARM1 would be a bigger die than that, but probably not that much bigger. So that's cool. I used to know which things were here. I think this is the instruction decoder, and that's like the ALU and control logic, and that's the registers and stuff. So you can see even this ARM1, an old, there's Visual 6502, we'll look at the 6502 as well. The ARM1 still had like the same 16 registers. That was like a feature of the ARM1. And that's one of the features of RISC computing, is that you have more registers because you need to store more stuff temporarily while you're doing things with your instructions. You're doing multiple instructions to get the same result. In CISC computing, it was more like you get something from memory, add it to something in a register at the same time, and then put it somewhere else in memory immediately. Like things would all happen in one complicated instruction, which can speed things up, but it makes the architecture a bit more complicated. Ooh, a transistor level simulation of 6502. This will be fun. How do we get it to work? There's an Apple One. Here's our 6502. So you can see this one's only got the accumulator there, X and Y index registers, SP, and PC. Ooh. I wonder what this program's doing. I should read the user guide. Anyway, you can go and play with these things. They're cool. I'll have to get my Replica 1 to work for Thursday. And now I think I've got time for questions if anyone's got one. Otherwise we'll wrap it up early for the day. Amazing. We've never wrapped up early before. It's because I've been very efficient in previous weeks. Just find those SIMD instructions to tell you about. I don't think anyone's going to jump in for a question. Ooh. That's okay. I was just going to prove to you that we have those SIMD instructions, because I can look in the documentation and look at our list of instructions. the DSP instructions. These are the SIMD instructions. 32-bit multiply, 30-bit multiply, 16-bit signed multiply with single accumulator, dual 16-bit signed multiply returning difference, all these weird things, extract 8 bits and sign to extend to 32 bits, pack and unpack, quad 8-bit unsigned saturating addition, UQ8, add 8. Someone's asking me about advantages in terms of efficiency of RISC-V versus ARM. I have no idea. I'm not not that much of a CPU architecture aficionado. I'm sure that there are relative differences, but also you say RISC-V versus ARM. Well, which ARM and which RISC-V? There's a lot of different CPUs that are within these things. ARM have many different CPU designs. Yep, exactly. Nick Milbrandt has a really good suggestion that we have the special topics code course code COMP2300. I'll just put this on the screen, it's interesting. COMP2300 at ANU. This course is running next semester and has 4 classes simultaneously. Laptop ensemble, that's my class. Algorithmic verification, computer microarchitecture, and quantum computing. Folks, if you have space and you want to do a third year, a 3000 level course that's going to be really exciting, I encourage you to choose one of these. They are all going to be amazing. Of course, I recommend Laptop Ensemble, which is an incredible course. I'll go to the Laptop Ensemble website. Of course, there's Laptop Ensemble. And collaborative course in sound and music computing. But if you're not interested in that and you would also like to learn about how different CPUs work, go and look at computer microarchitecture with Scheib. Or you could, if you want to look at how future speculative quantum computers could work, go do that. And if you want to learn more about algorithmic verification, go look at that course with Peter Höfner. Quantum, someone's ready for quantum computing. I think it's weird, but I think it's possible to do multiple of these simultaneously. So if you are willing to, obviously the Galaxy Brain version will be to do all 4 simultaneously in one semester. That might be inadvisable, your brain will melt. But they're all going to be really, really fun. They're all happening this upcoming semester too. Okay, we will come back to some Replica 1 demos on Thursday morning, and for now, yeah, prereq for MicroArch is 2300 indeed. For now, I will say adieu. And I'll speak to you folks in a few days. See you later.